the important thing I'd like to start out with is that the sea level rise issue is in fact something that affects us both on short time scales, like on hours, all the way to years and decades. And in the context of the more immediate things that the public really tunes into, events, extreme storm surge events like Sandy and Katrina really capture the public's attention. And in fact, what we have found is that because of the gradual rise of sea level, these events are becoming more and more destructive. And so it's a concern in terms of the immediate timescale events, which are very dramatic, that we need to deal with this topic, both in terms of understanding but also communicating to the public. And then on longer timescales, the problem shifts more to a question of gradual coastal erosion, beach erosion, like what happens in Ocean City, or the very gradual inundation along the coast. And then one of the things that is less noticeable but is incredibly important is the fact that the slow rise of sea level is destroying a lot of the coastal wetlands. The rate of rise is fast enough that the plants can't keep up, and they're actually being drowned, so that we're literally losing wetlands massively along in some areas. And this is going to have eventually a very dramatic impact. So that, again, my point is that we're having the issue of sea level rise has a spectrum of impacts from short to very long time scale. So that's a preface to why we want to make observations and understand the mechanisms that are driving sea level rise. And for that, there is our premier system is in fact a series of satellites. A series of satellites that have sequentially been flown from 1992 to the present. This is a program of satellites that was initiated by NASA and its French counterpart, the French space agency CNES, in '92. And it was followed with a similar satellite in 2001 called Jason 1, and it was followed in 2008 by what we call Jason 2. And there was a shift between Jason 1 and Jason 2. Going to Jason 2, NOAA, which is an operational agency as opposed to a R&D type of agency, NOAA and its European counterpart, EUMETSAT, which operates the meteorological satellites for Europe, joined with NASA and CNES. We actually operate Jason 2, but NASA and CNES are the leads for Jason 2. Moving forward to very soon, hopefully in mid next year, we're going to launch Jason 3. And now we've actually completed the transition. Jason 3 will be led by NOAA and EUMETSAT. We are actually 50-50 sharing between the two agencies. And NASA and CNES are still involved very substantially. But this is essentially taking an R&D type activity and operationalizing it for the indefinite future.
Are the other satellites still functional, or do they get phased out?
Well, they die eventually. And I'll show you that to you in a minute. And I'll get to that in a second. So they are intended to be sequential, but overlapping. So what we have coming out of this satellite is a continuous global record. Now, what does this satellite do? It is a radar set that sends pulses down, that bounce off the sea surface. We measure the travel time. That gives the range between the satellite and the sea surface. There's a couple of other measurements involved, but in the end, what we wind up with is a measure of sea surface height variations as a function of time and space. And we can do this very precisely. We can actually measure down to about the centimeter level, which is kind of wild considering that the satellite is up at about 1,300 kilometers, flying at 17,000 miles per hour. I'm mixing my units here. But we can do this very, very precisely. And it orbits the Earth in a near polar sense as the Earth rotates underneath it, and it effectively samples the entire globe in 10 days. So what kind of results do we get out of this? And the results in terms of the sea surface height differences, this is a picture. Actually, what I'm showing here is the result just from last week, a 10-day period. What you're seeing up here is actually an animation that runs over, it should be running at 10-day intervals over all of 2014. And the color scale is not my choice. Blue is high with about 30 centimeters. Brown is low as minus 30 centimeters. And what you see is what I consider an incredibly dramatic picture. There's all sorts of structure on all sorts of scales. The big, long, banded features that you see in the Pacific Ocean, those are changes in sea level caused by the seasonal changes in the major currents in the equatorial Pacific. The splotchy stuff, the smaller splotchy stuff, those are what we call eddies. They're either high or low sea levels, and they are directly analogous to the high and low pressures that you see in the atmospheric weather maps. So when the weatherman comes on TV and says we have a high here and we have a low here, he's talking about atmospheric pressure around which the winds will blow. Well, the analogous thing is we have currents in the ocean that circulate around these highs and lows. And so this is literally the weather map of the ocean, which we capture on a 10-day time scale from the adjacent satellite.
Why 10 days?
Well, because it's only sampling in a narrow band, it can't cover the whole globe simultaneously. And so we basically wait for the Earth to rotate slightly, and then it samples in a different place along the globe. I could have, basically it fills in sort of like a bird cage of sampling, and it only completes it in 10 days. Now you can fly satellites with different repeat orbits. Some other satellites might repeat like 30 days, or some satellites might repeat in 3 days. If it repeats in 3 days, then the sample spacing is wider because it just fewer opportunities to look. If you have a longer repeat period, then the sample spacing is narrower. This is chosen to optimize for sampling the ocean. What I'd like to spend time talking to you about is all of the uses for this data, because it has an incredible number of applications. Just like the atmospheric pressure field is applied for all sorts of meteorological work, this is applied for all sorts of applications, including hurricane intensity forecasting. The currents that we get from this are used in what Zdenko was talking about, the Coast Guard search and rescue activities. They use this data for their modeling activities. This is used for tracking where oil spills will go. This is the fundamental data set used for El Nino predictions because it actually maps the entire Pacific Ocean all in one shot. It's used for fisheries research. I could go on and on. There is a whole collection of things. But that's not the subject of this talk. If you take this picture and just average it, you get the average difference in the height of the ocean relative, in this case, to a 20-year mean. And when you do that, you get a completely different picture. And the completely different picture, which you see on the panels here, is the change in sea level, global mean change in sea level as a function of time. Each of these dots is a 10-day sample, and the different colors represent the different satellites. And going to your question about the overlapping, the intention is that we want the satellites to overlap because we're trying to make these incredibly precise measurements. And intercalibration between the satellites is very, very difficult. So we actually launch and fly the succeeding satellite to fly 1 minute behind the older satellite. And we do this for 6 months. I mean, it's It's an amazing thing that we can do that, but we're actually flying so close that we effectively sample the identical ocean. And it's this that allows us to get the kind of intercomparison that creates this time series that we're seeing here. Once we've accomplished that intercomparison, then what we do is we move the older satellite into a slightly different orbit to get a denser sampling of the ocean. But eventually that satellite dies.
Is Jason 1 still in commission?
Pardon?
Is Jason 1 still in
No,
commission?
Jason 1 died in...
No, I see.
No, actually you can't tell from the plot, but it died last year.
That was right.
Can you describe what it means to die as a satellite? Pretty esoteric.
The battery stopped working. In the old satellites, they used to have tape recorders. We don't have tape recorders anymore. You could have a memory malfunction. Usually it's, it could be any kind of electronic problem.
But they stay in orbit, right?
Yes, actually that's another topic because
Space junk, yeah.
space junk, which turns out to be, well, let me just answer her question. Space junk turns out to be a serious problem because most of these satellites are at 800 kilometers. We fortunately, for reasons like accidentally, we put our satellites up at 1,300, which turns out to be space junk heaven because there's nothing there. So we don't have to worry about space junk. But there is a treaty Europe, I think it's now U.S. law that we have to decommission our satellites, either send them down or put them up into what is referred to a graveyard orbit. That's essentially an international agreement, I think. Yes.
So would it be correct reading this that you have not had an unscheduled failure of one of these satellites because each one has overlapped from the one prior? So you have not had an unscheduled dying satellite, have you?
Well, eventually, we don't decommission them. We let them run as long as we can use them.
But you've never had one fail before you could get the other one up.
Right. And part of the planning there is the engineers plan these and say this satellite we'll plan it for a 5-year lifetime. Then it lasts 6, 7, 8 years. We don't know. The systems degrade on it, and so it gets risky. But for climate purposes, we absolutely want to get the overlap. I mean, these are expensive satellites, and so obviously redundancy becomes a money issue. But we absolutely need the overlap, otherwise the data loses its value. So what you see is a rather surprising picture because in some sense it looks remarkably simple. It's a linear increase. Well, it is and it isn't as simple as it looks because the rate, which is around 3 millimeters per year, which is a little bit thicker than a nickel, that happens to be about 50% faster than the rate measured over the last century. Now, it gets complicated to make the comparison, but basically we're using tide gauge data from the last century. But we have ways of making the comparison work. And we're pretty confident that there has been an acceleration between the last century and now. And so this is where we are now. And the 2.5 inches is what was the total sea level change over 20 years. And if you went back a total of 120 years, it would be about 10 inches. Which again, doesn't sound dramatic, but the beaches are fairly flat in a lot of places, and 10 inches makes a huge difference. Okay, so in a sense, this picture is concealing something which is a bit surprising because if you look at this data, the very same data, instead of a global mean, you put it out in terms of a map of local trends, goes crazy. It's completely different. This literally is the same data, but now what we're seeing is the spatial distribution. And it says that, in fact, sea level rise in a local sense is very, very different from region to region. And I'll just highlight a couple of areas. This particular plot is over 10 years, not 20 years, but the 20-year plot isn't very much different. And you can see along the east coast of the United States, sea level is rising fairly rapidly. And yet along the west coast, in a relative sense, sea level isn't doing much of anything. In fact, it may even be dropping a little bit. And so there is this dramatic difference in terms of what the local problems are, because in fact, sea level rise is not a uniform, as in total, is not a very uniform process.
So why, actually, if this is what you study, like why?
Why?
What's the difference, East Coast versus West Coast?
Well, to explain that gets pretty geeky, but the reason why we want to know that is we want to know, okay, is the sea level going to continue to drop forever along the West Coast? And the answer is no. You know, we can explain some of this difference. For example, some of the reason why the West Coast is dropping is because the wind fields over the Central Pacific are drawing water towards the middle of the Central Pacific. So you see that red blob in the middle of the North Pacific? That's partly water that's been drawn away from the West Coast of the United States. This is part of a long-term climate variability of a thing called a Pacific Decadal Oscillation. And this can change and will change, and when it changes, that water will flow back to the West Coast. So there is a reason for looking at this, because it gives us a problem, it gives us an insight into, you know, what may happen in the future. And you can only tell that by studying the problem globally. Yes?
So is your job here, when I say you, meaning the agency, purely observational monitoring kind of work, or at some point are you allowed to make recommendations, or that's only at the request of Congress or another agency? Like, what is the dividing line between observing and monitoring than actually saying, well, we need to do this in order to prevent this kind of disaster or the environment getting into worse shape?
Okay, well, you cross a certain divide at some point. I'm a scientist. I study, I observe, I explain. I could even be, if I was in the business, I could even possibly make projections. But I can't, you know, advise in the context of policy. Are you familiar with the IPCC reports? This is the Interparliamentary Intergovernmental Panel on, right, I always get it scrambled. Anyways, they actually go to the point of providing projections upon which, you know, agencies may make recommendations, but that ultimately becomes a political decision.
I'll say that part of our National Ocean Service will use data from some of our other more scientific parts of the agency and work with coastal managers and look at how and you'll hear it a little more in the next presentation, but how is sea level changing in local communities? What products and services can NOAA take from some of our science and help the communities give them the baseline science? So in your community, what's the sea level doing? If once you start mapping it using GIS and looking, okay, under a 1 foot sea level rise, what will it do to your community? 2 foot, 3 foot. So we're not the ones to do local policy or tell people, you have to, either other agencies do that, other state, local governments. We're here to provide the science and the support and the tools and products that help decision makers, in theory, make informed decisions.
Yeah, Billy will get into that more, but in the context of, for example, Sandy, I mean, that was a giant wake-up call, and Mayor Bloomberg, is immediately on the press saying, well, we have to plan for the future. Well, what is he going to plan with? He needs the data that NOAA and can provide to inform the planning process. So, yes, great.
Well, just looking at the map, so a lot of the scary red dots, concentrations are sort of in Southeast Asia, right?
Right.
Like Indonesia, Papua.
You want me to explain that?
One is, why is that specific area so
Hot?
rolling? And two, given that they are islands off the
Right.
coasts, it's problematic for them, I would imagine, more so than a lot of other nations.
Well, in fact, in terms of the long-term threats, the island nations of the Pacific are probably the scariest because they have practically no sea level, no elevation above sea level. This is in large measure a byproduct of the fact that over the last decade, we've been in a sort of a semi-permanent La Nina, which is the opposite of El Nino. And I can go on and on about this stuff because it's a research area of interest in. But during the La Ninas, the winds blowing across the Pacific tend to be stronger than normal, and they literally pile up water in the Western Pacific. So that is, in part, a piling up of water just because of the winds.
And is that a climate change versus a climate anomaly? Do you know, is that something that's a trend line, or is that something that just kind of coincides with this time?
Okay, if you'll let me go ahead, I'll come back and
Okay.
answer that in a second, because I think I know what you're getting at. Okay? Anyway, so the point is, when scientists don't know what they're doing, they make a model. Okay? This gets to your answer, by the way. So, I mean, literally, that's what they do. And this isn't too far different than what we really are after. The idea is you want to think about what changes the sea level or your bathtub. And there's an input, there's an output. Let's, for the sake of discussion, say that those things are shut off or they are equal, so you're not worried about those changes. So how can you change the height of the bathtub? And one way you can do it is you can heat the water. And believe it or not, we're heating the ocean. In fact, about 90% I'm going to get in trouble, 90% of the surplus heat, which I won't define, is going into the ocean as opposed to any place else. The ocean is a vast reservoir of heat. And so what we're actually doing is heating the ocean, causing the ocean to rise. Another way of raising the sea level in the ocean is by melting ice. And so if you take ice, particularly, and I'll get this into this a little bit further, and melt it and dump it into the ocean, it spreads out very, very quickly, causing the ocean to rise. So these two, in my clever little model here, have contributed to the sea level rise. And it turns out that those two components actually are the dominant components of sea level rise. We have global sea level change, measured by Jason, and we have changes in the ocean warming causing density changes. And we're going to get that from Argo, which you've been introduced to before. And we're going to measure the mass change of the ocean using another satellite system called GRACE. And we combine these two, the Argo and GRACE, and we look to see how it relates to the total sea level. And does it add up to combine and answer that? I'm going to make a caveat here because we're talking about ice melt of continental ice. The ice has to be on land. Melting sea ice doesn't figure into it because it's already in the water, and Archimedes' principle says it's already factored in. Now, actually, let me go back a step to your question about, which I think was getting at the answer, at the question of, well, the winds push the water around in the ocean. That doesn't change the global mean sea level. That's just pushing water around, okay? And that's important in terms of predicting local sea level, but it doesn't address the question of what is causing the total global problem. Now, is that close to what you were asking?
Well, I was asking sort of like this La Nina phenomenon that we're seeing, is that attributable to a broader climate change issue, or is that like sort of an anomaly that this particular La Nina cycle has created that isn't necessarily related to the bigger picture?
The historic, we know from various ways of constructing records that El Niños and La Niñas have occurred for centuries and longer. And we've even known that sometimes they don't occur for long periods of time, and sometimes they occur more frequently. This happens to be an unusual period where, for a decade, the winds have been more than usually strong going to the west. Can that be attributed to climate change? Probably not, because it's within the range of what we would call normal variability. So, no, I wouldn't, I don't think anybody would claim that that's an artifact of global warming.
But I think in terms of, how does global warming affect, these cycles of El Nino and El Nino? Is this really, it's an active area of research that nobody knows at this point?
Yeah, I guess my answer to your question wasn't the original answer. I wanted to say that the winds play a role, but in the sense that they push water around, but it isn't one of these fundamental processes that I'm talking about here. Okay? So yes?
So when we hear news that Pacific Islands are disappearing, and we see the dramatic footage of
Right.
rising seas, that's happening in part just because of this La Nina effect, and it could be cyclical. So
Yes.
while we understand that sea level is rising gradually, those particular places that are now being flooded could, in 10 years, have more land.
Yes.
It could go the other way.
Yes.
For a while.
But only in a relative sense, and probably only for a little while, because I think the projections, which we have a fair degree of confidence in, say sea level will generally rise long term. But you're absolutely correct. What is happening now is aggravating the problem, but that could lessen. But it's not an excuse not to take action.
So then, without making recommendations, but what are the options of action? Like, what could potentially curb this from a scientific standpoint?
What could potentially
From
curb sea level rise?
Yeah.
We halt it. Or are you asking what could happen?
No.
How do you
What?
stop?
Just scientifically, what can you do to stop it? This sounds really bad and not, especially if you own real estate.
Geoengineering, right? That's been
You have to stop the warming.
Yeah. And what are the inputs from warming? Greenhouse gases.
Right.
That's what
I think I'll conclude with
Climate
a
change
point
sounds
that relates to what you're asking for. Anyways, so I constructed my bathtub model. I said, I think I can get there by using these various inputs. The Argo program has already been introduced to you. It's a marvelous tool because it does sample the upper 200 meters. The ocean's 2,000 meters. The ocean's about 4,000 meters deep. This is analogous, incidentally, to the radiosonde networks. These are the balloons that meteorologists put up in the air, and it provides a density profile. So there is the Argo program, and it measures density in the upper ocean. And there's this other program, which it would take me a half an hour to explain, and I'm not going to do that. It is a pair of satellites that measure the gravity variations as they fly over. And from these two data sets, we can essentially construct time series. And what do we get? And I don't know if graphs like this are terribly useful to most people. Scientists love them. What this is a measure of the time change of sea level in black, measured from JSON. And then the blue line is what we got from Argo. It's the equivalent change in sea level due to the warming of the oceans. And the red line is the equivalent change in sea level globally in the mean due to as measured by GRACE. And the purple line, which you can barely see, is sitting almost on top of the black line. The purple line is literally the sum of the density line and the mass line. Voila, we've done it. We've explained sea level rise in a global mean sense. And it's surprising that we just needed these two parameters for explaining it. The important thing, at least from my standpoint, is that the mass change is 2/3 of the total signal. That means we're really, really having an impact in terms of ice melt. Okay, so just like that other plot that I showed sort of hit a lot of important stuff, if you look at the changes in terms of their, in a map sense, what you get is a more complicated picture, not unexpectedly. The plot in the upper left is what the density changes in terms of sea level look like over a decade, and it has that funny non-homogeneous structure. The lower left is the mass change due to GRACE. That's surprisingly very uniform. It's high. It's about 5, it's up, close, maybe somewhere as close to 5 millimeters per year. And it's uniform. And the reason why it's uniform requires an explanation that has something to do with the fact that the ocean can equilibrate very rapidly to dropping water in. It sort of travels at the speed of a tsunami, actually. And so that's why it all looks uniform. So then if you add the upper left plot to the lower left plot, you get the plot in the lower right, which looks nearly identical to the Jason plot. And so we're now in the process of explaining in a broad sense the whole sea level rise signal. This is a little different than prediction, or it's a lot different than prediction, but it gives us the ability to actually see what's going on and explain what's going on.
Wait, so,
Go ahead.
oh, sorry. I thought I heard a voice. So wait, so Jason is with the La Nina phenomenon you spoke of a few minutes ago, but the bottom right one, that is absent of that sort of La Nina, because that's the density and the mass of the Jason is with
Jason is everything.
right, and the one on the bottom right is absent. The sort of
No. The bottom right is the sum of the two left plots,
right.
and it looks very similar. So it says that density variations and ocean mass variations equals the signal that we see in sea level.
Right. So the bottom right one is absent of sort of. Is it absent the La Nina effect?
No, that's where things get a little hairy. The La Nina effect is partially folded into the upper left one.
Okay.
So that's why
Okay.
it's in there, but it's not as obvious. Okay, bringing up the wind variations creates this problem in giving a talk. So, what I wanted you to see is these fundamental pieces of the puzzle. So why am I so scared about the ice? And the reason I'm scared about the ice is because there's a lot of evidence nowadays that the polar regions are experiencing a lot of ice loss. And there was just this article in the Washington Post last week. Basically what's happening is warm water is undercutting these ice shelves, which are then sliding into the ocean and then melting. And we don't know if this is going to accelerate or not, but it's clearly a very important issue, both in Greenland and Antarctica.
Would that count as land ice or sea ice?
It counts as land ice as long as it's still fixed to the land. It's like having a ledge that sticks out over the ocean. It's not floating. And what happens is it melts from below and breaks loose. And it's sort of like greasing the skids. And then the big worry is if you do this enough, you can start to accelerate the movement of glaciers into the ocean. The numbers for Antarctica are there's 70 meters of sea level rise in the ice in Antarctica. But that's not going to happen for thousands of years because that's literally 3-4 miles of ice. But all you need to do is start nibbling away at the margins and you could create a significantly greater problem. We've probably gone over time. So to summarize, this is sort of geeky, but sea level rise poses a severe threat both in short and long time scales. We know that it's accelerated over the past century, that it's largely due to ice melt, and we're expecting this to continue and perhaps accelerate. And complicating the U.S. picture is how the wind changes affect the local situation. And we have the observing systems now, which we didn't, 20 years ago, we didn't have the observing system. In fact, the Argo system and the GRACE systems are only really come online in the last decade. This is a plot of the total sea level change over the Jason time period, 2 decades. And it's pretty dramatic because it gives pretty ample evidence that sea level rise is a global problem, and it is just very much apparent everywhere. So, oh, and actually, I don't think I lost the journalism gene entirely. I got a stack of magazines from the Oceanography Society. This is a special issue that I co-edited with difficulty. And you're welcome to take one if you want. It has a wide range of articles in it. I recommend, there's a article in there on how to prepare for sea level rise, which is towards the end, which is really fascinating.
All right. I'll take one question, and then we're going to have another sea level rise presentation, so some of your other questions may be answered, but I'll do.
All right, so with the 10th anniversary of Hurricane Katrina coming up, what are some story angles that you think are worth looking into? I mean, there's going to be so much coverage, but from the scientific perspective, what are some ideas based on your research that you think are worth looking into?
Well, I mean, there were some very clear engineering failures that led to the flooding.
The lens.
Yeah, and so the question is, you know, did the Army Corps of Engineers fix that? And there's an interesting thing about Katrina, which actually ties to the altimetry. The altimetry actually showed that that as Katrina was passing over the Gulf of Mexico, that it went over a warm eddy, which meant that it was able to suck more energy out of the ocean, and it ramped up to a Category 5 hurricane in the middle of the Gulf. But by the time it hit land, it had dropped down to a Category 3. So all that devastation was the result of a Category 3 hurricane, not a Category 5, the biggest ones. So in a sense, the question is, well, geez, what would happen if a Cat 5 storm hit? Can I take 1 minute extra?
Sure.
Okay. Somebody asked a question about connection to the Navy. There's a story that you're all probably familiar with Google Earth. The base map in Google Earth, where it shows the ocean, shows the bottom of the ocean, the bottom bathymetry. That's largely from satellite altimetry. It's a bit of a complicated story to tell you, but basically we're able to measure indirectly a lot of the structure of the bottom of the ocean. Our group published a map of the bottom bathymetry in the Indian Ocean, where the MH370 plane was believed to have gone down. Of course, we haven't found it yet. But that map is largely based on altimetry. Only 5% of that area had ever been surveyed by ships. And the U.S. Navy uses our data for bathymetric purposes also. So it's a side story.
Yep. Thank you.